The final Newton-Cotes integration formula that we're going to consider is Simpsons 3/8 rule. Again, this was covered in Eng 1060, so I'm not going to spend a lot of time on it. So the idea of Simpsons 3/8 rule is that we have 4 data points, x1 through x4, and function values at each of these points, f1, f2, f3, and f4, and we're going to fit a cubic polynomial, given by this expression here, to these 4 equally spaced x values. Again, mathematically, we're going to say that the exact integral is equal to the integral from x1 to x4 of our function, and that's going to be equal to approximately the integral from x1 to x4 of our polynomial that we're fitting up here. If we plug the polynomial into the integral, we get this, that's the integrand, and then analytically we can integrate that and get the following expression. So it's just 1/4 ax to the 4th plus 1/3 bx cubed plus 1/2 cx squared plus dx, evaluated over the range x1 to x4. Again, we won't go through the detail, but it's fairly straightforward to show that the Simpsons 3/8 rule integral is equal to the width of the total interval, across the 4 points, x4 minus x1 divided by 8, multiplied by the function value at the first point, plus 3 times the function value at the second point, plus 3 times the function value at the third point, plus the function value at the 4th point. And it's probably not a bad exercise for you to go through and prove this. It's not hard. Again, we introduce a spacing h, which is equal to the distance between each pair of points, or x4 minus x1 divided by 3, because there are 3 segments. And then we can write Simpsons 3/8 rule as the integral is equal to 3h on 8 multiplied by this sum of the function values. So that's Simpsons 3/8 rule. The truncation error in Simpsons 3/8 rule is approximately -3/80 times the 4th derivative evaluated somewhere in the interval times h to the 5th. So again, it's order h to the 5th, and it's much more accurate than the trapezoidal rule. In actual fact, it has very similar accuracy to Simpsons 1/3 rule. But again, just like in all of the other cases, we would never use Simpsons 3/8 rule with just 3 intervals. We would always split up our domain into multiple intervals. The composite Simpsons 3/8 rule looks like this. It's a somewhat more complicated formula because now the 1, 3, 3, 1 added to the 1, 3, 3, 1 gives a sequence that looks like 1, 3, 3, 2, 3, 3, 2, 3, 3, 1. Okay, so we have the first point and the last point contribute just with a single multiplier. Some of the other points, the points at 2, 5, and 8, 3, 6, and 9 contribute with a 3, and these other points with indices 4, 7, 10 contribute with a 2. So implementation of this formula is a bit messy. It's also messy because the number of segments we must have must be a multiple of 3. And that's usually a little bit more limiting than making them a multiple of 2. Often, Simpsons 3/8 rule will only be used if you have an odd number of segments. You might use Simpsons 1/3 rule for most of the segments, and then just for the last 3 you'd use Simpsons 3/8 rule. Typically you wouldn't use it for any other reason.